next. All right. So as a reminder, light is an oscillating electromagnetic field, right? So here is our lovely picture of light, okay, where we have the oscillating electric field going up and down, and then perpendicular to that, we have an oscillating magnetic field, okay? So this is the electric component, and B is the magnetic component, okay? And so as you might imagine, when we have electrons spinning, right, that can influence a magnetic component of light. And also photons are spinning, okay? So how do we deal with this? And what's happening with this, okay? Well, first, we recognize that, going from a p orbital to an s orbital, that's legal, okay? I'm going to transition away from this really quick, and I'm going to show you a picture of what we mean, why we're able to go from an s to a p orbital, okay? So if we think about this s orbital right here, and we're shining light on this thing, and so this is showing you light that is polarized in the z direction. So we'll make a note here that this is PZ, in other words, ML equals 0, okay? So if we're shining light of all polarizations at this atom, right, there's going to be all of the angles bombarded on this 2s orbital, okay? But specifically, there will be a vector in that light, right? If you imagine, right, it's got all polarization vectors available, there will be a z component of that light that lines up with the z component of the atom, okay? And as you can see by this picture through these oscillations, right, we're going to get not only an oscillating electromagnetic field from the light itself, but also from this transition from a 2s to a 2p, we're going to have an oscillating dipole moment in the actual molecule. And that's why light is able to interact with these things. Okay? But what about going from this 1s to 2s? Well, these are both spherically symmetrical. And so there's no change in dipole moment going from this s to s orbital. And that's the reason why we can't have L equal to 0 in technicality, right? L is plus or minus 1, okay? So we have to have, so for an atom or molecule to interact with that field, it must possess a dipole oscillating at that frequency, okay? So as we, right, bombard our molecules with light, or as it emits light, the oscillating electromagnetic field of light itself must be oscillating at the same frequency that the dipole moment of the atom is oscillating at. So, in other words, just like we observed in vibrational spectroscopy, for us to have a transition dipole moment, this expectation value must be not equal to 0 for an allowed transition, and for a forbidden transition, it would be equal to 0, okay? And so now I'll just remind you a couple bookkeeping things to consider for our math, okay? So now what we're dealing with here in this particular operator, we're dealing with the full d tau, okay? So in this wave function right here, my psi, I'll remind you, right, this is equal to the radial component times the angular component. So we need the full d tau, all right? And specifically, we have to indicate which dimension we're talking about, whether it's a dipole moment in x, y, or z, which is related to this picture right here, right? If we have a dipole moment that's aligning with, let's say, the z-axis, we would use mu z. If we're talking about transitions to a 2px or a 2py, that's okay. We can do that, right? But remember, the 2px or the 2py will be oriented 90 degrees relative to that 2pz, depending on which one we're talking about. Which means in the case of using a completely, what's the word I'm looking for? So if we're using a light source that's non-polarized, right? So if we have a light source that has all of the polarization angles available to it, right? Then we could excite the mu x, the mu y, and the mu z, right? We could do it all three. So, but typically when we make calculations with this, we generally just look at one dimension at a time to make life easier. Okay? And what I'll remind you, because our d tau is dependent on r, theta, and phi, when we use these operators right here, we have to substitute their polar spherical coordinate transformation. All right. So for example, suppose I wanted to evaluate mu z operator from, let's say, 2pz. So this picture that we've got going here, right? 2pz to 2s, or 2s to 2pz, right? Either way, it's the same. So then that means I'm going to have my 2pz wave function. And then now, we know that mu z is equal to negative ez. Well, that's going to have to be negative er cosine theta as my operator, right? I've got to replace the z with the coordinate transformation, okay? And then now on the other side, this will be the 2s orbital, okay? And as it turns out, I'll just supply to you the value of this. What's pretty cool about all these dipole moments, just like you saw in exam 2, they actually turn out to be fairly simple equations. So this one turns out to be negative 3e a naught, the Bohr radius, divided by z, the charge. Okay? Which actually turns out to be quite large. That ends up being 7.66 dBi. That's a large dipole moment. And the larger this dipole moment is, the more intense our spectroscopic transition is. Okay? So if we were comparing two different transitions, right? Let's suppose I got a peak that was this tall versus a peak that's this tall. The taller peak, right? The more intense peak has a larger transition dipole moment. The energy, right, where it appears on the spectrum is dependent upon which orbital and which energy level it came from, okay? So moving forward. So we talked about this picture right here. I'm not going to go into this in hideous detail, but we can, so I showed to you where this L plus minus 1 and ML equals 0 or plus minus 1 comes from. So for the ML equals 0 or plus or minus 1, so we have to transition from like orientations, right? So from a PZ to a Z or a DZ, right? Or from a PX to a DX, for example, okay? Okay, good, excellent. So typically we observe ML equal to 0 in polarized situations because we generally will polarize something along the Z axis, just as a convention, okay? So now all of this detail right here, this actually gives the mathematical proof for the fact that delta L equal plus or minus 1 or delta ML equals 0 or plus or minus 1. This is the mathematical proof that makes these things work. And I just wanted to point that out, and I'm not going to spend too much time with this, okay? But now what I do want to go back, I want to come back full circle and talk about the our hydrogen spectrum, right? We talked about this at the very beginning, the Lyman series, the Balmer series, and the Paschen series. Well, you notice now, look, there's no D to S transitions, right? Remember, for L, right, this is 0, 1, and 2. And L can only be plus or minus 1, right? Look, we've got transitions that go from P to S, okay? We've got transitions that go from D to P, but we don't see any S to S transitions, We don't see any P to P transitions or D to D, right? We have to have a change in dipole moment. So even though for hydrogen and hydrogen only, all of these levels are degenerate, right? This was N equals 1. This is N equals 2, including, right, 2s and 2p. This is N equals 3, 3s, 3p, and 3d. Even though they are degenerate, it's been shown with polarization studies, as well as studies involving magnetism, so where you look at how an applied magnetic field influences the spectrum. Those types of experiments confirmed these rules that delta L must be plus or minus 1, okay? And so for hydrogen, this is really hard to work out. But when you look at things like sodium or magnesium or calcium or other common elements that are hydrogenic in nature, and by hydrogenic, like sodium plus, right? It's a full shell, okay? Then it works really well, and we can observe these quantum numbers.